Hey everyone, welcome back. Ready to dive into some seriously cool AI stuff today?
Always ready for a deep dive.
Awesome. So, we're going to be tackling how AI can be used to solve these super complex equations called partial differential equations, or PDEs, those equations that govern like pretty much everything.
Yeah, PDEs are kind of a big deal. Think about it. They describe how things change over time and space, like how heat spreads in your coffee cup or the way air flows around a plane wing.
See, I knew there was a reason I love coffee, but seriously, solving these PDEs traditionally, it's kind of like, well, a massive headache.
Totally. Think giant grids, tons of calculations, super computationally expensive, not exactly a walk in the park.
Which is where this super cool new approach comes in, right? It's called physics-informed Gaussians, PIGs for short.
Catchy, right?
Totally. But let me get this straight. Instead of those rigid grids, we're talking about using Gaussians, those bell curve things.
Exactly. And here's the cool part. Those Gaussians, they can adapt and move around.
Wait, what? So it's like they're learning the solution organically?
You got it. It's like having a smart, flexible net that adjusts to the problem. Each Gaussian has these parameters that control its position and width. And during training, they actually morph and shift to fit the solution.
Okay, I'm already mind blown. But wouldn't that make things more computationally complex, like all those moving parts?
Well, there are some clever tricks to manage that complexity.
Yeah.
One key thing is that Gaussians have this thing called locality.
Locality.
Yeah, it means each Gaussian basically only affects things in its immediate vicinity. So
Yeah.
you don't have to calculate interactions between all of them, just the nearby ones.
Oh, okay, so like a divide and conquer strategy.
Exactly. Each Gaussian tackles its own little piece of the problem. But it gets even more interesting. The Gaussians, they don't work alone. They team up with a lightweight neural network.
Whoa, hold on. Combining adaptable Gaussians and the inner network, why?
Think of it as a two-step process. The Gaussians capture the overall shape of the solution, and then the neural network comes in and adds the fine details, like precision and refinement.
Okay, that makes sense. Two heads are better than one. But okay, so how are they actually performing? Are we seeing improvements over traditional methods?
The results are super promising. They tested these pigs on a bunch of different PDEs, the ones you'd see in physics and engineering, and the accuracy is amazing. In some cases, up to 50% improvement, and they're using fewer parameters, which means faster training times.
50%. That's huge. So faster A&D, more accurate. What kind of impact could this have on, real world stuff?
Think about it. Better weather forecasting, designing more efficient airplanes, even understanding how materials behave at the molecular level.
Wow, okay. I'm officially on board with the pigs revolution. But what makes them tick? What are the key factors driving this success?
One thing is the number of Gaussians you use. More Gaussians generally mean more accuracy, just like using a finer mesh in traditional methods.
So it's about finding that sweet spot between accuracy and computational cost.
Precisely. And the neural network plays a critical role too. Adding even a small neural network for refinement led to a big jump in performance. It shows how well these two components can work together.
So we're not replacing traditional methods, but kind of like supercharging them with AI?
Exactly. It's about finding the right combination of techniques for the job. Now, remember how we talked about those trainable parameters that control the Gaussian's shape and position?
Yeah, like the controls for the morphing magic?
That's right. Those parameters are key to the adaptability of pigs. They can be fixed, which is simpler but less flexible, or they can be learned during training, which is more complex but allows for a lot more freedom.
I have a feeling letting those Gaussians move around freely turned out to be a good idea.
Spot on. Letting the positions be learned was essential for reaching that high accuracy. Like, those Gaussians know where to go to get the best fit for the solution.
Okay, my mind is officially blown. This is amazing. There's one more detail. I'm curious about those covariance matrices.
Ah, yes. The covariance matrices. They control how spread out each Gaussian is.
And how does that affect things?
Well, there's a trade-off. You can have dense covariance matrices, which offer more flexibility but need more computing power. Or you can go with diagonal matrices, which are simpler and faster, but have limitations.
So which one wins?
Interestingly, they found that both dense and diagonal matrices produced very similar error levels in their tests.
So even with simpler matrices, you can still get awesome accuracy. That's really cool.
It is, and it opens up some exciting possibilities for making pigs even more efficient, which actually leads us perfectly into the next part of our deep dive. All right, welcome back.
Time to see those pigs in action. We've talked a lot about how they work, but I'm really curious to see how they handle some real-world problems.
You know, one experiment that stood out to me was their work with the Klein-Gordon equation.
Okay. I have to admit, the name sounds pretty intimidating. What exactly is the Klein-Gordon equation?
It's a pretty fundamental equation, actually, in relativistic quantum field theory. It describes how particles behave at super high speeds, close to the speed of light. It pops up in all sorts of areas, like cosmology, even condensed matter physics.
So not something you'd use for, like, everyday calculations, then?
Probably not for your grocery shopping list, no. But for understanding the universe, super important. And it's a tough one to solve, computationally speaking, of course.
Okay, so how did the pigs do? Did they manage to crack it?
Oh, yeah, they did.
Mm.
In fact, they outperformed another cutting-edge method called SAPNN, which also combines neural networks and physics constraints. Pigs got about 10% better accuracy on the Klein-Gordon problem.
10% might sound small, but I bet in this field that's a pretty big deal, right?
Oh, yeah, absolutely. It's a significant improvement for sure. But it's not just about theoretical elegance. They deliver results. The researchers also tested pigs on a flow mixing problem.
Flow mixing.
Yeah, imagine two fluids, say oil and water mixing together. Turns out it's harder than you might think to simulate that accurately.
I can imagine. You'd have to think about viscosity, density differences, the shape of the container.
Exactly. And as the fluids blend, you get these areas where the solution changes rapidly, and then other areas that are more stable. That's where the adaptability of pigs shines.
Ah, so the Gaussians can kind of focus their computational power where it's needed most.
Right. Like having a smart grid that refines itself. And the results, they were impressive. Pigs produced solutions that were super close to the reference solution, much better than other methods.
It's like watching those Gaussians dance, capturing all the complex movements. So much more intuitive than a rigid grid. And hey, didn't we talk about dynamic Gaussian allocation?
Yeah, where pigs could actually add or remove Gaussians on the fly, right?
Exactly.
The researchers started exploring that with something called separable pigs, or SNAPA-gigs. They leveraged the structure of certain PDEs that can be separated into different dimensions.
Hold on. So instead of one big pig, you could have multiple smaller ones, each tackling a different dimension.
Precisely. Like a divide and conquer strategy for PDEs. And since each SBs is working on a smaller, simpler problem, they can be way more efficient, especially when you're dealing with problems that have many dimensions.
So for those specific kinds of PDEs, spikes could be a game changer, huh?
Oh yeah, for sure. The results showed that spikes were much faster than traditional PNNs, especially for those multi-dimensional problems.
Okay, that's amazing. But, we've been talking about what's called forward problems, where you know the equation and you're trying to find the solution. What about those inverse problems, where you're trying to figure out the missing pieces?
Inverse problems are tough. It's like having the finished puzzle, but trying to figure out what the picture is supposed to be.
Exactly.
But guess what? Pigs can handle those too. They're that flexible. The researchers tested them on an inverse problem with the Allen-Cahn equation.
Okay, remind me, what's the Allen-Cahn equation again?
It describes how different phases separate, like oil and water in a vinaigrette. They had data representing the separated phases, and they wanted to use the pigs to estimate a missing parameter in the equation.
So like working backward from the result?
Exactly. And, the pigs nailed it. They estimated the parameter accurately and did it much faster than traditional PNNs.
Wow. Okay, so pigs are looking good for both forward and inverse problems. They're like the multi-tool of PDE solving. But there's one thing that's always a challenge, especially in physics and engineering, high-dimensional problems.
Ah, yes, high-dimensional problems. As the number of dimensions increases, things get exponentially more complex.
Right, more variables, more complexity. So how do pigs handle that? Just throw more Gaussians at the problem?
Well, they could, but there's a more strategic approach. They use something called stochastic gradient descent in the dimension. Basically, instead of updating all the parameters at once, you randomly pick a few dimensions to update in each iteration.
So you're focusing your computational effort on smaller chunks of the problem.
Exactly. And for high-dimensional problems, it makes a huge difference. They tested this with pigs on both the Allen-Cahn and Poisson equations, and get this, in 100 dimensions.
100 dimensions. Seriously. And how did they do?
They did amazing. They got good accuracy, even in that crazy high-dimensional setting. Proof that they can scale to problems that would completely crush traditional methods.
Okay, I'm sensing a theme here. Pigs are breaking barriers left and right. But there's one experiment I'm really curious about, the lid-driven cavity problem. It's a classic fluid dynamics benchmark, right?
Yep, that's the one. Imagine a square container filled with fluid, and one wall is moving. It's like stirring your coffee, but way more scientific.
Uh-huh, exactly. So what happened?
Well, they put pigs head-to-head against another method called PGCN, which uses a fixed grid. It's adaptability versus rigidity.
Okay, who came out on top?
Pigs, of course. They matched the reference solution beautifully, even better than PGCN. And they converged to that solution way faster, too.
Okay, so it's another win for the pigs. Accuracy, speed, versatility, they seem to have it all. But are there any downsides, any limitations we should be aware of?
Good question. No method is perfect, right?
Mm,
Pigs do have some limitations. One is the computational overhead of those adapting Gaussian parameters.
right, keeping track of all those moving parts takes some extra effort.
Yeah, but remember, they could use that locality thing to help reduce the number of calculations. Still, it's something to keep in mind. But there's another limitation that's even more interesting, that fixed number of Gaussians at the start. What if that wasn't fixed?
Oh, that's that dynamic allocation idea we keep coming back to, right?
Yeah.
Imagine if they could add or remove Gaussians as needed during training. That would be mind-blowing.
Right, like giving them even more control over their resources. It's a huge area for future research. Imagine pigs that could intelligently decide where to add more Gaussians to capture complexity or where to remove them for efficiency.
That would be like a team of artists working on a giant mural, each focusing on a specific part and coming together to create the whole picture. All right, we've covered a lot of ground here. In our final part, we'll wrap things up and dive into some of those potential future advancements. All right, we're back for the final part of our deep dive into these amazing physics-informed Gaussians.
It's been pretty mind-blowing, right? Seeing how these adaptable Gaussians are changing the game for solving PDEs.
Seriously, they've totally shifted my perspective on how AI can tackle these, fundamental problems in math and physics.
And we're just getting started.
Exactly. Before we get to all those exciting possibilities, though, let's recap what we've learned about pigs for our listeners. What are the key takeaways?
Well, I think the biggest one is that pigs provide a whole new way of thinking about how to represent the solution to a PDE. No more rigid grids. We've got these flexible, adaptable Gaussians that can morph and fit the problem perfectly.
It's like they're learning the solution from the inside out.
Right. And remember, they don't do it alone. They've got that lightweight neural network working alongside them, adding that extra layer of refinement and precision.
It's a perfect partnership. We've also seen how they can be even more efficient with things like SPIGs, exploiting the structure of certain PDEs.
Exactly. And their versatility is amazing, tackling both forward and inverse problems, opening up tons of possibilities for all sorts of fields.
From simulating fluids to, understanding the universe at its core, it's incredible.
It really is. But as with anything new, there's always room to grow, right? And that's where the really exciting stuff comes in. We've talked about dynamic Gaussian allocation, where pigs could add or remove Gaussians as needed.
Yeah, giving them even more freedom and control. It's such a cool idea.
Right. Imagine they could start with a small number of Gaussians and add more only where it's really necessary.
It's like those adaptive mesh methods, but with the power of Gaussians.
Exactly. Or we could even use reinforcement learning, where the pigs learn over time how to best allocate those resources.
So they're not just adaptable, they're learning and getting smarter all the time. Mind-blowing.
It's a wide open area for research, full of possibilities. And it's not just the number of Gaussians either. We could explore different types of Gaussians, maybe some that are stretched or skewed to better capture those complex features.
Or even bring in other basis functions, expanding their toolkit even further.
Exactly. Finding the perfect set of tools for each specific problem.
It's like having a master artist, choosing from a whole palette of techniques to create a masterpiece.
And I think that's what's so exciting about this field. We're seeing this fusion of traditional numerical analysis and cutting-edge machine learning.
Two worlds colliding to create something truly revolutionary.
And that fusion is going to lead to some incredible breakthroughs in how we solve those equations that, govern pretty much everything in our world.
So for our listeners, as we wrap up this deep dive, the takeaway is clear. Physics-informed Gaussians are a huge step forward in PDE solving. They're already achieving amazing things. And the potential for future innovation is just, limitless.
It's a field ripe for exploration, and I think we're only just beginning to see what these pigs can really do.
It's been amazing exploring this with you. Thanks for joining us on this deep dive. Until next time, keep those Gaussians morphing, those neural networks learning, and those PDEs solved.